So, we are discussing basically the what are the information so one can get from the wave function, okay. So, from solving Schrodinger equation for hydrogen like atom, we have got basically the eigen equation, where eigen function psi n l m, that is in terms of R n l, a radial part, and the angular part L m theta and phi m, function of angle phi. Okay. So, this is the eigen function, and if you apply operators, say Hamiltonian on this, so we will get Hamiltonian on this. So, we get basically Hamiltonian on this, you will get En psi n l, or you can write this one. Okay. So, this is the eigen equation, this psi n l m, this is the eigen function, and En is the eigen value. Okay. In this case, it is energy, because we applied operator on this, that is energy operator, Hamiltonian, that is energy operator. So, so that En, that specific value of this En, we have seen En equal to minus mu z square e to the power 4 by 2 n square h cross square, okay, which is same as we got from the Bohr model. Okay. And now that what we are discussing, what else, what benefits we can get from solution, from solving this Schrodinger equation for the same hydrogen like atom. So, as I mentioned that we get this wave function, this psi n l m. So, this gives a lot of information about the system. So, what are the information we can extract from this wave function that I was discussing? So, I have already shown you that this is basically wave function. So, to extract information, we have to we take probability, so its probability density. So, that psi star, and here we are getting this radial probability density, that is basically R dependent, R n l star, R n l, right. So, this probability density we have seen that PR, that is this probability to find the electron along a given direction at location between r to r plus dr. So, that is basically PR dr. Okay. So, but another probability density parameter we have defined, that is DNL or dr. So, that is that we have integrated over the theta and phi. So, that means this DNLR, it is equal to r square DNL square. Okay. So, this how it comes, that I have described. So, this is the probability to find electron between spherical shell of radius r and r plus dr. So, between r and r plus dr, two spherical cells. So, between these two spherical cells, what is the probability to find the electron? Okay. So, varying the r, we can get probability at different radius, okay, at different distance from the nucleus. Okay. So, that is what I was discussing, and as I mentioned that when NLM, that value increases, so these wave functions become complicated, but first few wave functions for smaller value of quantum number. So, this I have shown you. So, here you can see for n equal to 1, 2, 3. Okay. So, corresponding L, that is if n equal to 1, L equal to 0, M equal to obviously 0. So, this wave function, form of wave function is this. Okay. So, for n equal to 2, L equal to 0 and 1, and corresponding M equal to 0 plus minus 1, and this is the wave function that I have described. Okay. Here I have we can see that for L equal to 0 and M equal to 0. So, it is independent of this wave function, it is independent of theta and phi, there is no term of theta and phi. Okay. Here L equal to 0, M equal to 0. Okay. So, in these two cases there is no theta and phi term, but for L equal to 1 and M equal to L is not equal to 0 and M is not equal to 0. So, in that case this wave function depends on theta and phi. Okay. So, here also 3 0 0, this also independent of theta and phi. Okay. Now, if I take just radial part, so it is r dependent part. So, then you know already I have shown you that radial part basically RNL, its the form is like e to the power minus r, some other constant and n is there. So, it depends on r. So, exponential term, another is r to the power L, okay, and polynomial in r. Okay. So, now if we consider this radial part, so what so this I was discussing. So, RNL is e to the power. So, just I have neglected this normalization factor. So, here e to the exponential e to the power minus z r by n a 0 r to the power L and this polynomial. Okay. So, this polynomial, this Laguerre polynomial, associated Laguerre polynomial, it is called, it is a polynomial of degree nr. So, nr is basically here n plus L minus this 2l minus plus 1. So, this basically n minus l minus 1. So, these the degrees of, it is called the degrees of this polynomial. So, this number is this, what is the degree? It is nr. Okay. So, this is the number degree of polynomial. So, this basically this degree of polynomial, it signifies that the number of radial nodes. Okay. So, so I already I tried to so this one, if I plot them as a function of r, so this wave function radial with this e to the power minus z or a0, right. So, for r10, for r nl, so 10 for 10. Okay. So, this so exponential, I have drawn exponential curve, this one fine. Now, the probability density, radial probability density r square r nl square, here 10 r 10 square. Okay. So, it will be like this. Okay. So, how it comes, that I try to explain you. So, here actually this exponential term, that you have so I have shown you. So, r10, so exponential term is there. Okay. And in addition, so when I am making it square and this r square, okay, so it means this r10, so what are the exponential terms? So, it will be more sharper because it is squared now, it is e to the power minus 2r minus e to the power minus 2 z r by n a0. Okay. So, that means its shape will be like this, and additional another term r square is there. So, that is the if you take y equal to, so this I have done y equal to e to the power minus x kind of things, and another part is there y equal to r square or x square. Okay. So, it is the basically hyperbolic parabolic. So, its parabolic function will be like this. Okay. Now, if you multiply them, these two curves, so here it is 0, here somewhere you will get maximum. Okay. And it is going towards 0. So, at the end also it will follow this curve. Okay. So, if you multiply them, basically you will get this kind of curve. Okay. So, this tends to 0. So, this is the now your probability curve, Okay. If I okay. So, this the here just this r10 and corresponding the probability, radial probability density r square r10 square. So, this one can plot. Okay. Similarly, r20 also I have shown you that it has exponential term, another linear term is there. Okay. So, in this case, so exponential term, it will be I think this is r20, it has exponential term. So, if I just r20, if I plot r20, so it will be r20, it will be one exponential term like this. Okay. E to the power minus z r by 2 a0. Another, this is y equal to mx plus c Okay. So, this curve will be like this. So, its C is plus 2. So, it can be say like this. Okay. So, negative slope, it is at negative slope minus minus z a 0 r. Okay. So, now if you multiply these two, so what you will get? You will get, I think, if you multiply with them, so it will follow this. So, it will have some higher value, and then it is going towards negative. So, if we add this, so it will be like this, I guess. I have any other color? Yes, I have another color. So, if you add them, so you will get basically sorry, it should be exponentially. I think I have to. So, here you will get negative, and it is exponentially, it is going towards 0. So, if you multiply them, so it is a very small value. So, it will be like this. It's negative value, it will be negative. So, I think it will be 0. It is 0 multiplied with 0. So, I think it has to be like this. Like this. Okay, has to be like this. Okay. So that's what I have drawn here. So, I have drawn here, and corresponding, if you make square of it, so you will get this type of. So, this way, just taking the wave function as we have shown, one can plot, but as I told you, when this n and L value is higher and higher, m value is higher and higher. So, things become slightly complicated, but one can plot for a higher value also, taking help of computer programming, one can plot them. So, anyway, so here without seeing this wave function, I can also plot from this if I know the degree of polynomial, that is NR, if I know that one. So, for NL, in this case n is 1, L is 0. So, what will be the NR? NR is equal to n minus L minus 1. So, n equal to 1, L equal to 0. So, 1 minus 1 equal to 0. Okay. So, number of nodal point will be 0 for R N L, number of nodal point will be 0, means it will not cut R axis, and that is what is happening. For this n equal to 2, L equal to 0, n equal to 2, L equal to 0. So, n r equal to 1. So, number of nodal points is 1. Okay. So, it will cut R axis only once. So, that's what is happening. That's what is happening, right? This is the nodal point, this is the nodal point. Number of nodal points are 1. Similarly, for R N L, n equal to 2 and L equal to 1. So, n equal to 2, L equal to 1. So, here NR will be 0, right. So, number of nodes will be 0. So, this wave function, if you plot, it should be like this. Okay. So, from wave function, explicit form of wave function, just as an example, I have shown these two. Now other wave function also, this nature of the wave function one can draw just knowing the degree of polynomial, okay, from where you will get the number of nodal points. So one can draw, okay, and corresponding if you make them square. So here if I square it, I have shown that how it is coming. Similarly for other, if you take square of this wave function and r square, basically probability density. So it varies, it will varies like this, other one varies like this. So here also you can see this n equal to 3, l equal to 0. So number of nodal point is 2. So it will cut at this point and this other point. So nodal point are 2. Similarly, in this case nodal point is 1. So it will cut once. Other one, n equal to 2, n equal to 3 and l equal to 2, n equal to 3, l equal to 2. So nr equal to 0 means number of nodal points are 0. So it will not cut. So this is okay, it is varying like this, and corresponding variation, probability density variation, radial probability density variation is like this. So if you plot the probability density, radial probability density, so you are getting this. What does it mean? Its meaning is that this probability to find the electron is maximum at this point, at this radius r. Okay, it can so in Bohr model, what we have seen in Bohr model, we have seen that electron only can be found found in on a orbit, okay. So there are different orbit, okay. So in between there is no possibility to find the electron, but in quantum mechanics what we are saying, that is not correct. So it's basically electrons, it's not a particle, it's spreaded, it can be found everywhere, basically it can be found everywhere, but in some places to find the electron, it has maximum probability. So this curve is telling this is the radius r where it has maximum probability, okay. And others you can see this, it has here tiny peak are there, so small probability there, but it is negligible basically, but highest probability to find the electron for this state, it is at this position, okay. Similarly for this state, it is the probability to find out this. So here you can see what we are seeing, that L equal to 0, that is A state, basically L equal to 0, there is A state, L equal to 1 P state, L equal to 2 D state. So for A state, for only A state where L equal to 0, okay, L equal to 0 here, L equal to 0 here, L equal to 0 here, okay. For this case only, this wave function is not 0, it has some finite value, except L equal to 0. For other value of L, this probability to find the electron at r equal to 0 is 0, right, is 0. So means r equal to 0 means it is at its nuclear position, okay. At nuclear position, at nucleus, the probability to find the electron is basically is 0. Okay. But it is only exceptional case we are seeing in case of L equal to 0. Okay. For L equal to 0, so here is one can there is a probability to find the electron close to the nucleus. Okay. So, this wave function does not vanish at for L equal to 0, and this is very important. Later on we will see that this is very important to explain the hyperfine structure. So, as I described earlier, fine structure that is because of LS coupling. Okay. For L interaction between the L and S, spin angular momentum and the orbital angular momentum, and hyperfine structure. Again fine structure, after that this fine structure also it is splitted. Okay. The split this energy difference is very small, but one can see, one can measure this separation, and that is very small, although it is very small, but it exists. And what is the origin of this fine structure? That is basically interaction with the nucleus of the electron. Okay. So, if wave function does not exist, okay, near the nucleus, okay, so how this interaction will happen? So in that sense, hyperfine structure for S for this case where r equal to 0, but the psi wave function is exist, wave function is exist. Okay, and this give chance to interact electron with the nucleus, and as a result we get some splitting of the fine structure, and that is called basically hyperfine structure. Okay. So, what else information we can get from here? So, for L is not equal to 0, L is not equal to 0, RNL is basically proportional to Ln, because this term is there, Ln term this. So, when L equal to 0, so this term will not contribute, okay, only this term will contribute, but when L is not equal to 0, so this term will contribute. Okay. And this term you see for higher and higher L value, for higher and higher L value, and for smaller and smaller r value, means r tends to 0, when r tends to 0. Okay. So, this r smaller value. So, smaller value less than 1, if it less than 1, then if you, so then r square is greater than r to the power r cube is greater than r to the power 4, etc. So, this power, when increasing power, so this factor will be smaller and smaller. So, for higher value of L, so this will make this wave function smaller and smaller. Okay. So, that means when r tends to 0, so this existence of this wave function, it is a wave function will be smaller and smaller, and it will go to vanish. Okay. So, means for when r is not equal to 0, so probability to find the electron towards nucleus is negligible. Okay, is negligible, and that's what is happening. That's what is happening for L is not equal to 0. Okay. So, wave function it's negligible value, it's almost 0 for all cases, it almost 0 for all cases. Okay. Except L equal to 0. So, that is the things, and this is happening because, and this effect is more and more when L value are higher and higher. this because of basically this L is basically this angular momentum, right. So, because of angular momentum there is a centrifugal force. Centrifugal force means its electron is rotating. Okay. Now, for higher and higher L, what will happen? So, this centrifugal force will be higher and higher, means it will try to, because of this centrifugal force, electron this force will try to take away electron from the nucleus. Okay. So, that is why when L value is higher and higher, the possibility to find the electron towards nucleus, towards R tends to 0 will be smaller and smaller. Okay. So, these are the from wave function, radial wave function, these are the information one can extract. So, these are very important information. So, also one can find out the expectation value of the radius. So, what is the expectation value? How to find out? So, say position if we find out, so r psi star r psi, okay, and then you have to integrate over the range, and then you will get, if it is normalized. So, that way one can write. So, then you will get the expectation value of that of this position, or in this case it is radius. So, if one calculate this one, so dNLR, so this is the probability to find the electron between two spherical cell. Okay. So, now R, if I take this if I want to find out the expectation value of radius, so I have to take R. So, then if we integrate, so if you evaluate, then you will get this type of expression. Okay. So, this is the expectation value of radius, and here you can see that this part, if I just of this part, so it is, what is this, n square a 0 by z, right. So, that is what the same thing, this is nothing but the Bohr radius, right. This radius we obtain from Bohr model. What we obtain? N square a 0 by z. A 0 is I think h cross square by mu E square. Okay. So, that was the a 0. So, exactly from Bohr radius whatever, but in this case the expression value, it is not exactly the Bohr radius. Okay. Whatever the radius we got from the Bohr. So, it is different, and it depends on the L. Expectation value is like this. But if you find out the maximum probability of radial density, so maximum probability for radial density, we have seen that only for this, when L equal to, only for these cases where L have the maximum value for a particular n, L equal to n minus 1. So, for a particular value of n, maximum value of L is n minus 1. For maximum value of L, so here you can see this is the maximum value of L, okay, n equal to 1. So, L equal to n minus 1, so 0. So, it has only one maxima. Maximum value in this case, it is the one maxima. In this case, okay, this is the L equal to 2 for n equal to 1. So, this is the L equal to n minus 1. So, maximum value of L. For maximum value of L, we are seeing this only one maxima. Okay. So, for other cases this it is not one maxima, other maxima are also there, but out of them one is one predominate, okay, other are negligibly smaller. Okay. So, but in this condition, when L equal to n minus 1, if I for this case basically I can write r n L equal to n minus 1 r. So, r to the power L. So, now I have replaced n minus 1 exponential this term. Okay. So, this the so for highest value of L I can write this wave function like this. Now, corresponding density, radial density probability, one can write this r square into this. So, this ultimately you are getting this square means 2 n minus 2. So, this r square is there. So, r to the power 2 n exponential, it is square term 2 are there. Okay. This. Now, how to find out the maxima for a particular value of a parameter. So, in this case our parameter is r. So, if you differentiate it with respect to r and make it equal to 0, then whatever the value of r you will get or this parameter you will get. So, that is the value where you will get the maximum probability. So, if you evaluate this, so we are getting r equal to n square a 0 z. So, this is exactly the same expression as we got from the Bohr model. So, it is the Bohr orbit. So, here we can only tell so that at this radius we will get this this probability of the electron is maximum. So, that much we can tell, but in Bohr model it told us only on this orbit it will be find out, but in this case at the in the orbit okay. So, there will be maximum probability to find the electron, but it will not be only there, it will be other places also, but its probability is very less compared to the orbit. So, basically this from wave function we are getting the similar information whatever we got from the Bohr model. Okay. So, here you can see this is the maximum probability and the expectation value is slightly higher than this one, because this part is there. So, plus some extra additional part is there. So, that depends on L. Okay. So, for L equal to 0, so this part is 0. So, but then you are getting basically 1 plus half, okay, means 1.5 times of this radius or the orbit in the Bohr model. So, expectation value is higher than the most probable value, that is because of the asymmetry of the probability curve. Asymmetry of the probability curve is known. This is the asymmetry of the probability curve. So, expectation value and the most probable value. So, this is the most probable value. Okay. But expectation value is it's taking the average kind of things on this curve. Okay. And if this curve is symmetric, then we would get the same value, but since the curve is asymmetric, this curve is asymmetric because of that, because it extends longer towards the higher r value. So, that is why this expectation value is higher than the actual maximum probability value. Okay. So, these are the information one can get from wave function. So, I discussed about the radial part, about along the radius, along the distance from the nucleus position, what are the probability to find the electron. So, that I discussed from the radial wave function. So, in next class I will discuss angular dependence probability. So, I will stop here. Thank you.